Hello, my name is Joshua Fuller, and today I will be teaching you about optimization. Now, optimization, in simple calculus terms, is the finding of maximum and minimums of functions. It's a very practical way of doing it, though. So let's say you're a business, and you have a cost equation. You want to optimize that by finding the minimum of it. You want to find the minimum of the cost equation to minimize your costs. In the same way, it goes for a profit equation. You want to maximize your profits. And this will make a little bit more sense in a bit. And so let's go to a very classic problem, something I like to call the can problem. So you're a can manufacturer, and what you do all day is make cans, and you want to find the minimum surface area it takes to make a can that can hold 3 liters of material. And so 3 liters is 3,000 cubic centimeters. And since it is expensive, you want to minimize the surface area of the can to minimize the amount of tin you have to buy. So you need 2 equations for this. The first one you need is the surface area of a cylinder, and that is 2 pi RH plus 2 pi R squared. And this is the equation we're actually going to be minimizing. This is the equation we are going to be finding the minimum of. The second equation we need is the volume equation. And that equals pi r squared times height. And so if we go back up, we already know the volume, 3,000. And that can be useful when it comes to isolating variables, because right now our surface area equation has 2 variables, and you can't optimize with 2 variables. You need to isolate one. So let's rewrite our volume one. 3,000 equals pi r squared times height. And from this, you can easily see we can isolate one of our variables very easily. H. All you have to do is divide by pi on both sides and divide by r squared on both sides. And that gives you H equals 3,000 over pi r squared. Bang. So now we've isolated a variable. We can plug this version of H, this H in terms of R, back into our surface area equation, and then we'll only have one variable. So let's do that. I'm going to start a new page. Let's rewrite our surface area equation so we don't forget. Remember, it's 2 pi RH plus 2 pi r squared. And let's plug H into it. So we'll rewrite that as 2 pi r 3,000 over pi r squared plus 2 pi r squared. We can simplify that to 6,000 over r plus 2 pi r squared. And now we only have r's, and that's great. We can find the minimum of this equation to find the minimum surface area. And how you do that, and this is kind of the basis of optimization, is to find the derivative of the equation. Because from the derivative, you can find the zeros of the derivative, which give you the minimum and the maximum. And I'll explain a little bit more of that later. So on your calculator, if you click dr of 6,000, and this is, of course, to find the derivative, plus 2 pi r squared, you will get out negative 6,000 r squared plus 4 pi r. And now, back what I was saying earlier, the reason we want to find the zeros of this equation are because, from what we know about derivative, let me just draw a little fake function here. The derivative is just the slope of a tangent line. And so, logically, if the tangent line equals 0, if it has a slope of 0, as you can see by my example here, it will be at a max or a min. And so if we set this equation equal to 0, we get that x, or r, because r equals 5 times 3 to the 1/3 times 2 to the 1/3 all over pi to the 1/3. And that's a nasty answer. So you can just convert that to decimal. And when you convert it to decimal, you get 7.816. And so that's great. We just found the radius. And with the radius, we can find the height. So if you remember, height equals 3,000 over pi r squared. You plug r into that, and you get that h equals 15.6316. And that's great. Bang. That's how you do it. We just found the minimum surface area. We just found the radius and the height of the minimum surface area. A very important thing you need to remember is to go back to the problem and remember what it's asking. And so this problem has units. And units are very important, especially on the AP test. So in this problem, the units are centimeters. So we go back to our thing and add in centimeters. And remember, this is centimeters, not centimeters squared, not centimeters cubed, because radius and height are lengths, not areas, not volumes. And so this was a very simple problem. The derivative had one zero, and that zero happened to be a minimum. But in most problems, that will not be the case. So I'm going to do another problem right here. Something a little bit, it's easy, but it demonstrates my point more. So let's take the equation negative x cubed minus x squared. This could be a cost equation of producing some amount of units. So we want to find the minimum of that. So let's do that. You guys can probably find the derivative of this in your sleeve. It's just negative x squared minus 2x. And we can set that equal to 0. And anyone with 3/4 of a brain can figure out that is 0 and negative 2/3. And bang. But now we have an issue. We have 2 zeros of the derivative. In the last problem, we only had 1. So now we have to do what's called the first derivative test to figure out which is a max and which is a min. And the first derivative test it's very nice. It's very easy. You only need the first derivative, and if you have gotten the zeros of the first derivative, you probably already have the first derivative, unless you're cheating off your neighbor's test. But don't do that. We teach good habits here. So the first derivative test, you don't have to make a table, but it makes it much easier. To do the first derivative test, you find values around the zeros. So a value around negative 2/3. So negative 1. A value in between 2/3 and 0 is negative 1/3. And a value near 0 that's not below it is 1. Once we take these values and we plug them in to the derivative and find their sign. Are they negative or positive? Because that's all we really care about. And I'll explain more about that in a bit. So if you plug in negative 1, you're going to get a negative. You plug in negative 1/3, you'll get a positive. You plug in 1, you'll get a negative. And so if you look at my example here, I'll explain why that's helpful. So, fake function. Divide this up into what its zeros would be, because at these points where it's hitting the function, the derivative would be 0. And so on this, when it's going up, the derivative is positive, and then the derivative is negative, because it's going up, and then it's going down, and then it's going up, and then it's going down. So you can see at the points where the derivative switches signs, there's a max or a min. And when it goes from a positive to a negative, you have a relative max. And when it switches from a negative to a positive, you have a min. And that's how you can tell. So at 0, it switches from a positive to a minimum, to a negative, which means it's a max. And when it switches at 2/3 from a negative to a positive, it's a minimum. So for finding the minimum, using this data, we can figure out that negative 2/3 is the minimum. And that is the basis of optimization. And so when the problems you'll see, they will probably have a combination of the CAN problem and this, where it'll be a complex, it'll be a visual problem that you can see, but there will be multiple zeros of the derivative. And that is the basis of optimization. Thank you for listening to my presentation.